we're going to look at three more indeterminate forms that will only occur in AP Calculus BC. The first one is 1 to the infinity power. So the limit as x approaches infinity of 1 plus 1 over x to the x falls into that category, because 1 plus 1 over x, when x is infinity, is just 1, and we're raising to the power of infinity. So the next three limits that we're going to do with three different indeterminate forms will all follow the same pattern. We're going to take the natural log of the function that we have, find the limit as x approaches infinity in this case, or whatever the a value might be, of that new function with the natural log, which will allow us to remove the exponent and put it out in front. And then at the end, once we've found that limit, we're going to raise that number that we get to the power as a power of e. We're going to exponentiate it, and that will give us our final answer. So here we will look at the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x. This allows us to rewrite this as the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Now this indeterminate form is infinity times the natural log of 1, or 0, so infinity times 0, which needs to be rewritten so that we can use L'Hopital's rule with it. We'll have the limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over x. Now we're in the form 0 over 0. So using L'Hopital's rule, we'll end up with the derivative of the numerator, which should be 1 over 1 plus 1 over x, times the derivative of 1 plus 1 over x, which is negative 1 over x squared, over the derivative of 1 over x, which is negative 1 over x squared. The negative 1 over x squareds will cancel out, and we're just left with 1 over 1 plus 1 over x, which gives us 1 over 1 plus 1 over infinity. 1 over infinity is 0, so we end up with 1. But we're not finished, because this is only the answer to the limit of the natural log of our original function. So we have to exponentiate this, make this e to the first power, or e. The next indeterminate form that we're going to look at and use this technique for is 0 to the 0 power. So once again, we're going to take and look at the limit as x approaches 0 from the right of the natural log of x to the x power, which then allows us to remove the exponent and pull it out to the front. So we've now got the limit as x approaches 0 from the right of x ln x, which once again, as x approaches 0 from the right, ln x is negative infinity, and the x is just 0, so this is 0 times infinity, which means that we will rewrite this as the limit as x approaches 0 from the right of ln x over 1 over x. Now this is an infinity over an infinity, which is allowing us to use L'Hopital's rule to get the limit as x approaches 0 from the right of the derivative of ln x, which is 1 over x, over the derivative of 1 over x, which is negative 1 over x squared, which can be rewritten as the limit as x approaches 0 from the right of negative x squared over x, which is just the limit as x approaches 0 from the right of negative x, which is just 0. But once again, this is not our final answer. We need to go back in, and we need to exponentiate this, so we end up with e to the power of 0, which is 1, as our final answer. The last indeterminate form that we'll look at that will use this same method is infinity to the power of 0. So we're looking at the limit as x approaches infinity of x to the 1 over x. So what we'll do is we'll look at the limit as x approaches infinity of the natural log of x to the 1 over x, which we can pull the exponent out again, gives us the limit as x approaches infinity of 1 over x times ln x. Well, if we plug in infinity, the natural log of infinity is infinity, and x is just infinity, so this can be solved using L'Hopital's rule. We will take the derivative of the numerator. The derivative of ln x is just 1 over x, and the derivative of x is just 1, and 1 over infinity is 0, so we have 0 over 1, or just 0. But again, this is not our final answer. We have to go back in and exponentiate this, get e to the 0, which is 1 for our final answer.